Well, hello everybody. We're on to chapter 3 now. It's all about the cell. Now the cell has various organelles and various structures inside that the lab covers very in depth, very in detail. So for this I'm going to cover once again more of the physiology behind it, and most of the physiology occurs in the cell membrane. So I'm going to go ahead and draw a cell membrane for you. And the cell membrane is made up of modified fats called phospholipids. I believe we talked about these in chapter 2, but if not, phospholipids are a phosphorylated head of what we call glycerol. It is a carbohydrate, it's charged, but the tails are made up of fats, and they are non-charged, they are non-polar. And on the outside of the cell, there's a phospholipid, but on the inside of the cell too, there is a phospholipid. So what that means is that both the exterior and interior of the cell are lined with phospholipids. So what that does is it creates kind of a sandwich. If you think of a hamburger, you have the two pieces of bread. Those represent the glycerol heads, and then the meat and stuff inside the hamburger represents the fatty acid tails. So this lipid region is important because it's actually going to control what can easily pass through the cell membrane. So I'm going to draw just a small portion of the cell membrane with glycerol heads showing, because I mean you basically get the point. So these glycerol heads, they are going to line the inside of the cell, as I said, along with the outside of the cell. And in the center is going to be the fatty acid tails. I'm not going to draw these in any big detail because, as I said, you get the point. And the rest of the cell membrane, for simplicity, I'm just going to draw it as lines. So the cell membrane has some characteristics. As we talked about, is that polar molecules interact well with polar molecules. Non-polar molecules interact well with non-polar molecules. So that creates some very interesting characteristics of the cell membrane. Let me see if that's on these, where I put that on. Doesn't look like I put that on later, so we'll talk about it later. I was going to talk about permeability. So let's talk first about the things that are in the cell membrane. The one thing about the cell membrane is that it's mainly composed of phospholipids. However, even though these phospholipids line up like this, they're not going to be stable unless we add some things to increase stability. So there's a few things that we'll talk about here. And one, which I'll draw on a red line, one is the lipid molecule known as cholesterol. And cholesterol just kind of sits in at various points in the cell membrane. Let's draw it in red. The job of cholesterol, see, can you see this part? Yeah. So let's put down here components of the cell membrane. So the purpose of cholesterol is for stability. Cholesterol kind of resists temperature change. It resists the cell membrane from getting too cold and freezing over, or getting too hot and melting. It gives stability to the cell membrane. Next here are going to be very, very interesting molecules called glycoproteins and glycolipids. The book doesn't really go too much into their purpose. But what these are is that they are proteins. I'll draw them over here. They're proteins that span the length of the membrane, called a integral protein. And they either have, on top here, they either have a lipid-like substance or they're going to have a sugary complex. The function of these, there's many functions of, well, not many, but one of the main functions is cell identification. Each cell, virus too, has a very unique pattern that is specific to a certain cell type and to a certain, and it determines whether or not the cell is native or not. So we have glycoproteins and glycolipids. So say that this is glycoprotein / lipid. These are partially for cell identification. Now that goes with integral proteins. This is a class of proteins, and I kind of drew it over here. Integral proteins are proteins that span the length of the cell membrane. That means that they start at one side of the cell membrane and go through the next. This is a classification. It's not like an integral protein does this. It is a classification. It is a type of protein that is subdivided into different types of membrane proteins, one of which is going to be glycoproteins and glycolipids. So, how are cells connected? I'm going to draw this on the bottom here. They are connected through something called junctions. So this is a cell that we'll learn about this week. It's called an epithelial cell. And these cells do not exist alone. They actually link together to form things called tissues. So I'm going to draw some epithelial cells, and you'll notice that they look continuous. That's because some of them are rather, it's almost like they're stitched together with something called a tight junction. What these do is that they make the cells continuous almost. Continuous and rather impermeable to things moving through. That's why if you put water on your hands, it's not going to go straight into your body. It's because the cells that line the integuments, they are attached by tight junctions and they're very impermeable. Some things can pass through, like alcohols, for example, but not much. So these cells are linked together through what's called a tight junction. Now other cells, so other cells, they're actually connected through what's called a gap junction. And, so old. It's hard to pick these things up after a while. So gap junctions, what these are is they actually, think of them as almost a bridge, a skywalk between cells. So these are tight junctions, but these here are going to be called gap junctions. Examples of these are found in cardiac cells. Cardiac cells, they need to send electrical impulses from one cell to the next in rapid fire fashion. Because of that, the skeletal muscle cells are connected through gap junctions. They show up on histology slides as intercalated discs. You'll see that, I'm pretty sure, in the lab you'll be doing this week on tissues. Okay, so now we're going to talk more about membrane proteins, what their purpose is. We'll be talking about membrane proteins a lot because, as we'll talk about, not much on its own can pass through the cell membrane freely. Things like charged molecules cannot pass through the cell membrane. That's an issue because we need charged molecules like sodium and calcium to go in and out of the cell membrane. We also need things like large charged molecules like glucose, for example. That can't freely move through the cell membrane, so we need something that can help transport it. So these are integral proteins. The first purpose is going to be transport. So transport is going to be the first purpose. Now, to give you an example of transport, I'm going to put here a couple of examples of that. Let me make sure that I don't cover those later on. Yeah, I kind of do. So we'll just keep it very simple. So transport is the process of moving a certain molecule from one side of the cell membrane to the next. This is very important because cells constantly need nutrients and other large molecules in order to build things and perform essential functions. As I said, these charged and large molecules cannot pass through the cell membrane. Even water. Water has a poor ability to pass through the cell membrane. So we need these proteins that can help to facilitate transport. Next is going to be communication. Your cells are constantly communicating, constantly, about anything and everything. I wrote communicating, I mean communication. So close, yet so far. So cells are constantly talking to each other. The body systems are constantly speaking within themselves and others. We'll be talking about lots of molecules that are responsible for communication. One communication molecule is called epinephrine. What that does is it tells your cells to do things like it tells your cardiac cells to beat harder and faster. It tells your bronchioles in your lungs to open wider. And molecules like epinephrine, they don't actually do anything except tell a cell to change its behavior. So we'll be talking about that too, but the way that cells communicate is that you have a signal molecule, then a protein on the surface of the cell that receives that molecule and conducts it through the rest of the cell to form a response. And next is recognition. So as I was saying earlier, is that glycoproteins and glycolipids serve to identify cells. This is unique amongst species and individuals. The immune system from birth, from your birth, recognizes what cells belong to the cell, and it will not attack them unless you have something called an autoimmune disease. If you have a cell that is not recognized as the cell, it will get attacked. Okay. Now we're going to talk more about these phospholipids. I'm going to leave this diagram up here. So phospholipids have some very unique characteristics. They have a sugar head. It's more of a sugar alcohol, but what is called a carbohydrate head called glycerol that has a phosphate group attached to it. This makes it polar, meaning it can only interact well with polar molecules like water. That's why the inner membrane, the part with the tails, which is non-polar, it's non-polar / hydrophobic. That's why it hides from the water, because it doesn't want to face the water. It acts the same way as oil when it meets with water. And the head is going to be polar, and it's going to be hydrophilic, meaning hydro-loving. Hydrophobic means water-hating. That's why the polar heads face the exterior and interior of the cell, and the tails are in between the two polar heads of the phospholipid, as we see here. Because of this, there's only certain things that are permeable, as I said, the cell needs lots of things in order to function well. So we're going to have a list here, permeable and non-permeable. And it's more like what isn't permeable. Because basically what's permeable through the cell is one thing is going to be small lipid-based molecules. There are very small molecules made up of lipids, and an example of that's going to be steroid hormones. But they're so small, they can actually sneak between these charged glycerol heads, and of course, they can pass easily through the lipid layer because they're non-polar. So small lipid-based molecules can freely pass through the cell membrane. Many psychological or medicines used in psychiatry, many of them are small and lipid-based. That's because there's a very selective barrier named the blood-brain barrier in our brain, and only very specific molecules can sneak through, small and lipid-based, for example. Therefore, pharmaceutical companies spend a lot of money making their compounds small and lipid-based to make sure they pass into the brain easily. Other things are gases. Gases can freely pass through the cell membrane. Oxygen, carbon dioxide, for example. They can freely pass through the cell membrane. And last of all, and I put an asterisk by it, last of all is water. But that's only because it can move through water channels, which are always open. Channels are integral proteins that provide a tunnel. Aquaporins are a type of water channel that's always open, never closes. As we'll talk about, some channels open, some channels close. But aquaporins, water channels, are always open. And water, if you are to leave it with cells long enough, recall that water is a very powerful solvent, eventually a little of it will slowly start to get into the cell and get out of the cell. So water is technically permeable. But since aquaporins are all throughout cells and are always open, water is basically permeable. Now, what is not permeable? Okay, this pen has seen better days. What is not permeable? For starters, anything large. Macromolecules are examples of things that are too large to pass through. So I'm going to put down large substances. And this is impermeable by itself, not counting help with channels or carriers. Charged molecules like ions, they can't go through the non-polar layer. And also anything that has polarity, anything polar, which is, of course, most things. Because of that, the workaround, if you want to call it that, is integral proteins called channels and carriers that can help them to pass through. So quickly, we're going to talk about the types of channels and carriers. So the first thing I'm going to do is draw some channels. Draw them in green. So one type of channel is called it just is called a channel. But there's 3 different types of channels, which we'll talk about. So these are channels in green. So channels go through the span of the cell membrane and create a passageway. Think of it like a tunnel in a mountain. Normally you can't drive through the mountain, don't even try. But if there's a tunnel there, you can drive through. Channels are like tunnels. Now some of them are always open. So this type is always open. An example is a aquaporin, which is how water moves between the outside and inside of the cell. We also have channels called gated channels. We have gated channels. Gated channels are interesting. The gate is usually covering the channel unless a stimulus prompts it to move. So what are some examples of gated channels? Now some are going to be what we call voltage gated. Voltage gated. Voltage gated channels are like setting your thermostat to 70 degrees. As soon as it goes above 70 degrees, what's going to happen is that the AC is going to kick on. Voltage channels are similar. When the cell membrane is charged a certain amount, it is going to cause it to open. And if it leaves that sweet spot, I guess you could call it, it's going to close. Next is called a chemical gate. This is going to stay closed unless a signal molecule binds with a receptor and tells the gate to open. Think of it like a special badge that you have to show someone in order to have the gate to the tunnel open up. And last is going to be mechanical gates. The gate will open if some sort of external stimuli is applied. An example of that is a pain receptor. What's going to happen is that if you damage your tissues a certain amount, that force is going to cause the channel to open, which will activate the neuron and cause pain. Now, the last type, and we'll talk about some subcategories of these. The last type is going to be called a carrier. Carriers, they're a bit different. To me, they're kind of like ferries. They personally escort a molecule from one side of the cell membrane to the other. And what these do, I'll write this over here, it's carriers. These move large polar molecules, usually. Now, one thing to keep in mind is that channels and carriers are specific to one or few types of compounds or molecules. For example, these channels, there's a channel that only allows sodium to pass through. There's a channel that only allows potassium to pass through. With carriers, there's a carrier specific for glucose, to give you an example. So those are the classifications of transport proteins. And now that we've talked about the basics of the cell membranes, now we're going to go on to another very important topic called osmosis. Well, hello everybody. We're now going to talk about our next part of chapter 3, and that's going to be osmosis. You probably remember osmosis from either your high school days or if you took a general bio class. But osmosis is the movement of water through a cell membrane, more or less. So to start, I'm going to show you something rather interesting. You probably know that in your, if you already work in the nursing field, you probably know that if you are going to rehydrate someone, you give them a solution of about 0.9% saline. You don't give pure water. So I'm going to show you something interesting. Let's say that you have a container and you are going to have a red blood cell. Red blood cells have a biconcave shape, like this. Now let's say that I'm going to measure concentration in the water in terms of green dots. Now this is not realistic, I'm just showing you a concept. So what we are going to do is we are going to put in a solution, 0.9% saline. Now, what we found is that about 0.9% saline has the same osmolarity as the cell. So first of all, let's go ahead and define osmolarity since we're at it. Osmolarity is concentration of solutes in a container, or sorry, let's go with in a solution, and it's measured in osmoles, abbreviated OSM. In the body, we normally use milliosmoles, MOSM. So it's basically if you're going to do an equation, which you won't be doing any equations in this class, but it looks like this. It's going to be concentration over 1 liter of H2O. So to give you an example, let's go with those concentrates. Hold on, let me get some. I have these in my water on occasion when I feel like I need my life to be spiced up a bit. So you probably know that if you were to waterfall this in your mouth, it would not give you a very pleasant sensation. That's because it is very concentrated, extremely concentrated. Now, if you add it to your water, it's going to become more dilute because the concentration is going down. You'll have less molecules in the water when you add it to your water bottle than if you add it by yourself. So we talk about that in terms of osmolarity. The only thing that you really need to take from it is that the higher the milliosmoles, the more concentrated it is. And we'll be using that to compare both sides. For right now, though, we're just going to stick with this basic example here. So when you add 0.9% saline, which is measured in five molecules here in green, it's going to be the same osmolarity as the cell. So we call this term, let me make sure I have the correct terminology here. And keep in mind, I'm not going to be, I'm going to make it a little bit more complicated than you might like, but watch this lecture a couple times. I really get the gist of it. So we see here that the molecules are the same. Now, whenever we are comparing two sides, two environments, as far as osmolarity goes, it's going to be in terms of concentration gradient. So let's talk about a concentration gradient here. So concentration, we've already defined, is how many molecules are dissolved in water. The more molecules, the more concentrated it is. We know that a gradient is the difference between one side and another side. So what this means here is that the steeper the gradient with osmosis, the more different the concentration is between two sides, the more water is going to follow. The rule that you need to keep in mind is that water is always going to go to the area that's more concentrated. Water is always going to go to the area that has a higher osmolarity or more particles. If there is no difference, water movement is basically going to stay the same. That's not 100% true, but in terms of teaching, we're going to stick with that. So the unit of measurement that we use is milliosmoles, but it could be anything really. Milliosmoles is just one kind of unit. The concentration gradient determines how much water needs to move to balance out both sides. Water will not move if the concentration between the two environments is the same. So with this, we use the term isotonic. And it fits into a concept called tonicity. What tonicity means is related to cell shape or size. So when we talk about tonicity, we always relate it to the solution. So what we see here is that both sides are equally concentrated. Water is not going to move. We call this isotonic. Keep in mind, both sides are isotonic because we're comparing two sides. Nothing can be isotonic by itself. All right, well, let's say that the nurse makes a mistake. Let's say that she's going to inject a 1.5% saline solution. So now we're going to add more molecules to our container. Now, since we're just going to be counting dots right now, because this is just a teaching introduction, we see that in the solution, there is going to be 9 particles of sodium. Inside the cell, we see that there's going to be 5 molecules of sodium. Because of that, we've established a concentration gradient. The steeper the gradient, the more water has to move. What's going to happen here is that water is actually going to move from the cell into the container. Because recall that water always moves toward the more concentrated environment. So it's going to look like this. Water is now going to move out, and the end result is that the cell is going to shrink. So the cell is going to look like this. It's going to shrink and is possibly going to shrivel. That, of course, is really bad because if your cells shrivel, they can't do their job, they can't function, and they might die. So this actually, the irony is you'll be rehydrating the patient while dehydrating them and causing harm. That's why it's very important that when you enter the nursing field, if that's your goal, that you make sure that your calculations are right. Giving a patient the wrong medicine or the wrong concentration of things will get you dropped from your program in no time flat. Okay, so we call this hypertonic because we always relate this to the solution. You can't have both sides hypertonic. You can only have one side hypertonic. So because tonicity, we always talk in terms of the solution. This solution is now going to be hypertonic. A hypertonic solution is going to result in the cell shrinking. This is what happens normally in dehydration. In dehydration, you have the same number of solutes, the same amount of stuff inside your blood. The difference is there's not as much water. Since there's not as much water, the concentration goes up. Therefore, water is going to move from one environment to the next. Oh. All right, everyone, sorry about the delay. I forgot that we had a department meeting. Been talking about for years that I need a calendar so I can keep track of my life, and every year I don't do that because, you know, I want to make my life easier, and I can just make it hard and just speak off the cuff, right? All right, so anyways, I think I was at is that if a solution is hypertonic, that means that the solution is more concentrated than the inside of the cell. Result is that water is going to leave the cell. And what if we do the opposite? What if we decide to change it to where now the cell is more concentrated than the solution? So in this case here, the cell is going to have 8 particles of solute, and the outside solution is going to have 4 particles of solute. Now the solution is not as concentrated as the inside of the cell, so we call that hypotonic. And just to clarify, hypotonic means not as much solutes. Hypertonic means too much solutes. The solution is hypertonic. That means the inside of the cell is more concentrated. The result is going to be is that water is going to enter the cell. So it's going to look like this. And what's going to happen is that the cell is actually going to expand. And if it expands too much, the cell could actually burst. The cell could burst because it's so filled with water that the cell membrane can no longer stay intact. So that is the problem with a hypotonic solution. What's going to happen is that the cells could become so saturated with water that they burst. This is what would happen if you gave someone an IV with pure water. Now, I'm going to make things a little bit harder. So I'm going to draw our red blood cell again. And now we're going to talk about penetrating versus non-penetrating solutes. So here's the thing with osmosis. We must include the concentration after penetrating solutes have gone through. A penetrating solute is something that can freely pass through the cell membrane and balance itself out. To give you an example, a penetrating solute would be something like lipids. I'm just going to give you an example, but the examples I give, I could say sodium's permeable or potassium's permeable. That's not true in a real cell situation, but it's just, recall that we're just teaching concepts here. So let's say that black are particles that can freely move through the cell membrane. Let's say that red are particles that cannot pass through the cell membrane. So the goal is that you are trying to find which direction osmosis will occur and how much of a difference the concentration gradient is. So these conditions here tell you nothing. That's because the particles are not all balanced. As I said, the particles that I colored in black are diffusible. Now, one thing we'll learn when we talk about diffusion next, which will kind of add on to what we learned, is that molecules will keep on traveling until they reach equality throughout the two environments. So what's going to happen is that if there's 4 diffusible solutes, 4 penetrating solutes outside the cell, they're going to equalize until they're even on each side. What's going to happen is that half of the molecules are now going to enter the cell. And it's going to balance out to where there's 2 and 2 on each side. And at that point, these penetrating solutes are going to stop moving. If we look here now, our final balance is that there's 5 particles inside the cell and 6 outside the cell. That means water is going to end up leaving the cell just a tiny bit because the gradient isn't that much. With osmosis, the type of solutes do not matter as long as they can dissolve in water. So it doesn't matter, each of these solutes can be different. We're just curious about the total concentration, the total osmolarity. The type of solute does not matter. We just want to know the difference. With penetrating solutes, the biggest difference is that you have to balance them out before you determine the direction of water. In this case here, at the beginning, the outside of the cell was much more concentrated than the inside of the cell. As soon as we let the penetrating solutes equal out, we see that the difference is not as much and only a little bit of water left. So next after this, we're going to be talking about diffusion. All right, everyone. Well, welcome back. We're now going to talk about diffusion. Now, osmosis, which I drew over here just to help us review. Osmosis is the movement of water toward a more concentrated area. not all solutes can cross the cell membrane. If there is an imbalance, water will move toward the more concentrated side. In this case, water is going to move into the cell, causing the cell to swell and possibly burst. Diffusion is a different concept. So diffusion is when a solute can pass through the cell membrane and become even. All solutes want to become even. And I'm going to give you some examples of that. So let's say that this is going to be, we'll just say that this is going to be a container, and this is going to be a cell, a blood cell. Now, let's say that oxygen travels, of course, through the blood. So I'll illustrate here in a red line. So oxygen enters the blood through the lungs. When it passes through the lungs, the alveoli, which are the functional units, it is going to carry oxygen. We'll just say that here. At the site of this cell, there's 4 oxygen molecules. What's going to happen here is that a process is going to happen called diffusion, where solutes move until they become even. The greater the difference, the faster the movement. In this case here, there are 4 molecules, and 2 of them are going to leave the blood and enter the cell. This happens all throughout the body. Is that you have solutes, they're concentrated on one side, but then to become even, they're going to move and they are going to leave until they become even. In this case, as the oxygen molecules pass through the cells, oxygen is going to move toward the cells to become even. That's why blood can never become fully deoxygenated, because diffusion stops when the 2 environments become equal. Of course, to clarify that, the 2 environments will never become equal because cells are constantly using the oxygen. And this is kind of misleading too, because red blood cells do not need oxygen to make energy, but it's just an example. So anyways, why does this happen? Well, it has to do with the movement of molecules. All molecules buzz. They have energy. They buzz like this. So what they do, and by the way, this is a passive process. It doesn't require energy. What they do is that, let's say I concentrate them all on one side. These molecules are going to be buzzing around, and they're going to hit each other. Here, let me use a different color. They're going to constantly hit each other. Think of like playing pool, and you hit the main ball. I don't play pool much, and then it hits the other balls and scatters them. That's similar to what's happening here. These molecules are constantly hitting each other and pushing each other away, so they become wider. And this is going to keep happening until the molecules reach maximum distance between themselves. So to give you an example, I'm going to bring a cup of water. Okay, a beaker, a cup of water won't really be a good idea. So here is some water. And what I'm going to do is I'm going to put in some food coloring. I don't have food coloring present, so I'm going to put in orange crush. All right, so what you see here is that right now, all the orange crush is toward the bottom. By the way, it's very dangerous. I'm holding this by my computer. Now what's going to happen is that as I leave this alone, right now, the solids in the crush are hitting each other. And they're going to reach maximum distance until it becomes equal throughout the entire container. Now, the less food coloring I add, the slower it will become equal, become ubiquitous throughout the solution. The more food coloring I add, the faster it will become even with the solution. So I'm going to put this off to the side, and I'm going to check on it in a couple minutes. So I guess a good analogy you can use is, let's say that I were to take 30 of you, which I can't because of social distancing, but pretend there is no COVID-19. Let's say I was to take 30 of you and put blindfolds on you and put you in this room and instruct you, every time you bump into someone, you push them as hard as you can. What's going to happen is, if I bunch you all up, you're going to be pushing each other constantly, then you're going to space out as much as possible. That's exactly what happens here. These solutes are going to keep on hitting each other. So I'm going to box each time period until they become equal throughout the container. If given enough time, they will always become equal in the container. Now, the same thing happens in the body, because the goal is that cells need to get things. They need things that enter the cell, they need things to exit the cell. Because of that, they constantly need solutes to diffuse from the blood, where they're highly concentrated, to the cell where they're not concentrated. The opposite is true too. Cells need to take their waste products, get it from the cell where they're highly concentrated to the blood where it's not concentrated. That happens because of diffusion. No energy is required. So you're probably asking at this point, well, what happens if we need everything from one environment to the other? What if just passive diffusion is not enough? What if we need help doing something? Like, let's say we want to get all the solutes from one side to the other. Well, we will talk about that. So right now we're talking about diffusion. Definitely note diffusion is always a passive process. So now we're going to talk about factors that affect the rate of diffusion. Remember that diffusion is a passive process. We have no control over it. So the first factor is going to be the distance. The greater the distance, the lower the rate of diffusion. Meaning that the further the distance it has to travel, the slower it's going to take to get there. That makes sense. Now, this is what occurs in a type of hypoxia called pulmonary edema. What happens here is that you have the alveoli, which is in this black bubble here, and then you have the blood. So this is how it looks under normal circumstances. And oxygen is going to diffuse from the alveoli into the blood. But with edema, that space is actually going to grow. So it's going to look like this. And it's going to take longer to diffuse. So that is the main risk involved with pulmonary edema. All right, next is going to be molecular size. So size. The greater the size, the slower the rate of diffusion. Larger things move slower. If I were to ask you to drag a sled with a 25-pound plate versus a 100-pound plate, the sled that has a 100-pound weight will move slower unless you are very strong. In that case, they'll probably move the same. Next, we have temperature. Temperature. Not really a factor in humans because we have a constant temperature, but this is just a factor of chemistry. The greater the temp, the greater the diffusion rate. Heat makes things speed up. Gradients. Recall that a gradient is the difference between two sides. So gradients. The greater the gradient, the faster the rate of diffusion. That's because molecules want to become even. They want to travel from one side to the other. If they're bunched up in one area and not the other, then diffusion will happen faster. Next is permeability. Permeability is how easy it is for a molecule to pass through a barrier. So permeability. The greater the permeability, let's write perm, then the faster the rate of diffusion. An example here again is called fibrotic hypoxia. What happens is that the alveoli that I just drew, they become thicker, meaning that it's harder for oxygen to diffuse through. Next is going to be surface area. Surface area is the amount of space on on top of a container where things can enter and leave. So SA for surface area, greater the surface area, faster the rate of diffusion. Show you an example with that. Let me see if I still have balloons. Did I give them away? Hold on a second. I'll find a balloon. All right, I'm sacrificing a glove for you guys, which is like gold nowadays. If you want an example of surface area, think of number of doors in a room. The more doors present, the more people are able to get in and out of the room. It's the same thing with surface area on top of a cell, for example. The more space available on top of the cell or surrounding the cell, the more things can move in or out. So right now, this glove has low surface area compared to volume. Okay, that didn't inflate too well. So as you can see, as I blew up the glove, the amount of surface area on it increased. Don't worry, I'll find a way to save this glove. They're too valuable. All right, so the greater the surface area, the faster the rate of diffusion. Next we have, that's it. And as I said, compared with osmosis, osmosis is the movement of water. The movement of water is in concordance with the steepness of the gradient. Diffusion is they can cross the cell membrane and they will continue until the solutes reach equality. At that point, diffusion will occur no more. All right, so next we're going to talk about facilitated diffusion. Simple diffusion means that these solutes can easily pass through the cell membrane. Facilitated diffusion is different. And to answer the question, how do we get things into and out of the cell if they cannot naturally pass through? So I'm going to draw here a cell membrane. Remember, it has a double layer. And on the outside, I'm going to draw a non-permeable, some non-permeable solutes. One is going to be an ion. Ion is going to be sodium. Label Na+. I have a couple of sodium ions. The next one is a large molecule called glucose. I'll abbreviate it GLU. Neither one of these can pass through the cell membrane on their own. So, if we want to get glucose into the cell, we need something called a carrier protein. This protein spans the length of the cell membrane. And what it is it's a protein that kind of escorts the glucose from one area to the other. And it is specific only to one type of solute. In this case, this is a transport protein called a GLUT protein. And it's going to get it from one side to the other. Keep in mind, this is still an example of passive diffusion, meaning there's no energy involved. It's still going to move until it reaches equality, but it just needs to use this carrier protein instead of just traveling through. Now the next is a channel protein. Channel proteins just open or close. They can be gated or non-gated. We talked about this earlier in the lecture, so I won't go over these again. Just to review, so let me draw the gated channel first. So this here is a channel. Channels usually move small things like ions, and they can either be gated or non-gated. As I said, we'll say that this one's going to be open. Chemically gated channels open if a chemical molecule binds with it, causes it to open. Now, voltage gated, the channel opens if the electrical charge on the membrane reaches a certain point. And mechanically gated open in concordance with a mechanical stimuli, like for example, if you press on your hand, you feel pressure that has caused a mechanically gated channel to open and causes the neuron to activate. Okay, now there are different kinds of transport proteins. One is called a uniport. This here is a uniport. Uniport proteins, they only move one molecule. However, the second part is called a co-transporter. And with these, we have two examples. The first is called a symporter, which I'll write over here. Symporter. These move two molecules in the same direction. So for example, it can be sodium and glucose. And it moves them both in the same direction. Now, another example, which is one of the most important transporters, is called a pump. And we're going to get to this here. I'm not going to talk about these too much right now, but this is a pump. And this is an example of what is called active transport. Active transport. Active transport needs the energy molecule ATP. And what it does is it moves molecules against their concentration gradients. what it wants to do is get molecules completely on one side or the other. So what they do is that they move molecules against their gradients. The fusion, they naturally want to go from where they're bunched up to where they're further apart. So what it does is it takes molecules that are bunched up, like so, and they are going to completely move them against their gradient, like this. So what it wants to do is get molecules completely from one side to the other. Same thing would be here. So we see here, high concentration, low concentration. If these molecules had their choice, they would move to the area where there's less ions or less molecules. Instead, they're going to completely move into the cell. What this does is it creates an extreme imbalance. The goal here is not equilibrium. The goal here is disequilibrium, because it wants to move the molecules completely from one side to the other. It takes a lot of energy to do this, because you're trying to oppose molecules' natural response. They naturally want to become separated. Now you're doing something to keep them closer together. It's opposition. If any of you drive down the Canale gradient, you know that going down the gradient takes up very, very little gas. Going up the gradient, you're opposing gravity, you're using much more gas. That's why you need ATP, the body's fuel source. Sodium-potassium pumps, which exist to move both sodium and potassium against their concentration gradients, those use up a lot of ATP. About 60% of our daily energy intake is used just to power sodium-potassium pumps. They're that important and they're that ubiquitous. Now I have here two parts here in the study guide, primary and secondary active transport. This here, a sodium-potassium pump, uses ATP to move both these molecules against their gradients. So we need ATP here. We need ATP here. Sorry, that's backwards. We need ATP to move both sodium and potassium. However, secondary active transport, which I'll draw here, secondary active transport is a bit different. So this is a cell again. This is our secondary transporter. Make it nice and big. Actually, I kind of messed up on that. Let me redraw it. Why make life hard? Now, what secondary active transport does is it moves both molecules in the same direction. So this right here, secondary active transport. Let's abbreviate AT for active transport. So what I'm going to do here is I'm going to draw sodium in red. Now we see that there's lots of sodium on this side. Now, the other one we're going to do is green for glucose. See, there's lots of glucose on this side. So what we are going to do is, and this is a completely fictional example. Well, actually, no, this is not a fictional example. This actually happens. Sorry, I'm so used to saying that. Now, what we are going to do is we are going to use the natural movement of sodium to go down its concentration gradient. This requires no energy. What it is going to do now is glucose, because as we'll learn later on, oppositely charged molecules attract each other. As sodium goes down, sodium is going to go against this concentration gradient because it's dragged along by the sodium. Now this is still going to use some ATP, but less. So I'm going to put down ATP, but less. So what secondary active transport does is it uses the movement of one molecule going down its concentration gradient to move another molecule against this concentration gradient. This is much more efficient than primary active transport because you're using the movement of one molecule going down its concentration gradient. The movement of that molecule is going to pull along the molecule going against its concentration gradient. Because of that, you're using a lot less energy. Okay. So factors that affect carrier-mediated transport. Let's talk about these two. What are the factors that affect carrier-mediated transports? So this is the cell. Recall that carrier-mediated transport is necessary when we are dealing with solutes that need a carrier protein to travel. So I'm going to draw some carriers. And I'm going to draw some glucose. All right, so what are some factors? The first is going to be number of transporters. Think of transporters as checkout lines. The more checkout lines are open, the more customers can check out. Doesn't matter how many customers you have, the more customers you have is not going to make the checkout process faster. It's the number of check stands open. Carrier proteins are like check stands. So the more carrier proteins present, the more molecules can move through at once. If I were to add a fourth one, the process could work even faster. So how it looks here, if I were to draw a graph, what's going to happen is that the rate of the reaction, which I'll put here on the y-axis, versus number of solutes, we see here that if I have 3 transporters, what it's going to do is that the rate is going to increase really fast until all the transporters are occupied. At that point, the rate, which is how fast something happens, is going to stabilize at this value here. If I were to add a 4th carrier protein, we'll sneak it over here. Then we have more transporters present. We can move more molecules at once, and it is going to increase the rate of the reaction because there will now be a higher set point. Sorry, by rate of reaction, I mean rate of transport. Next is going to be saturation. This is similar here. The more proteins are saturated, then the faster transport will occur. Once all the transporters reach their saturation point, as we see here, the rate of transport can't increase anymore. So the number of transporters occupied, the faster transport is happening. Once they all become saturated though, once they all become full, then the rate of transport will even out. Think of it as top speed. If someone can run 8 miles an hour, the closer they get to their 8 mile per hour top speed, the slower they will accelerate until they stop accelerating. That doesn't mean they aren't still moving fast. It just means that they can't move any faster. Once they're at 8 miles an hour, it's analogous to the saturation points of the carrier proteins. And next is going to be competition. On occasion, some transporters can transport more than one type of molecule. Now, if we are trying to measure the rate of glucose transport, let's say that this transporter can move both glucose and I'll just say fructose. We'll do fructose in red. What's going to happen is that we've now put in a competition. So let's say that half of the transporters are going to be saturated with fructose and the other half glucose. What has happened here is that due to the presence of fructose that are binding to the carrier proteins, what's going to happen here is that the rate of glucose transport is going to go down because fewer glucose molecules can get into the carrier proteins because they're being occupied by the fructose solutes. What's going to happen here is due to competition, which I'll draw here in green, the rate of glucose transport is going to go down because there's more competition present. Now, if I were to add a bunch of fructose solutes like this, that means there's a greater chance that fructose will bind with carrier proteins other than glucose, and the rate of glucose transport will go down even more. Okay, next we are going to have what is called vesicular transport. So we'll keep this short and sweet. So one thing that you learned about in the lab that involves cellular organelles, cellular structures, is that sometimes the bulk transport of things is necessary through vesicles. And the first example of that is something called phagocytosis. Actually, let me erase this. So we have vesicular transport, which is bulk transport. That means you aren't trying to move small things. You're trying to move many large things at once. So this is called bulk transport. And we have a couple examples here. The first is called endocytosis. Endo means in, cyte means cell. Into the cell, the process of moving something into the cell. An example of that is going to be a macrophage, which is an immune cell that eats large things. It could be cellular debris, it could be bacteria. What it does is, let's say it's trying to hunt down a bacterium. What it's going to do is it is going to take its arms, these are called pseudopods, they're like fake arms. It's going to kind of hug the bacteria and bring it into the cell. Yes, a macrophage is a cell. It's going to encase it in a vesicle. And it's going to use enzymes called lysozyme to break down this bacteria into fragments. Now, at that point, we are going to do a process called exocytosis, where the vesicle, exo means out, is going to take the cellular debris and is going to merge with the cell membrane and is going to dump out the cellular contents. Endocytosis, something is taken into the cell. What happens is that the cell membrane is made up of phospholipids. So what happens is that it merges with the cell membrane and forms a vesicle because vesicles are made up of phospholipids. and it's kind of like a container. When the cell wants to export something, it takes a vesicle, the vesicle merges with the cell, then dumps out its contents. That's exocytosis. I have here receptor mediated and yeah, receptor mediated, let's go ahead and hold off on that. Receptor mediated, just to give you a brief outline of that, it's signaling molecules bind with proteins on the cell surface, and that tells them to undergo endocytosis. All right, right on. Now we have what's called epithelial transport. So when we talk about tissues, which is next chapter, it's also a lab you'll be doing, is one of the most dominant or predominant cells in our body is called epithelial cells. These are cells involved in things involving secretion, absorption, protection. So these epithelial cells, there's a top part called the apical side. There's a bottom part called the basolateral side. So this side, the apical side, faces toward the lumen. The lumen is like the inside of a container. So the apical side would, for example, be the epithelial cells that line the inside of your stomach, inside of your intestines, the lining of our esophagus, the lining in our cheeks. So that's where the apical side is. The basolateral side, which I did not finish here, is going to be facing what's called the ground substance, also known as, for example, connective tissue, and is also closest to the blood supply. That's the basolateral. Think of basolateral as basement. So the apical side faces some kind of surface. The apical side faces some kind of surface. The basolateral side faces the connective tissue and is closest to the blood supply. Transcytosis is the process of something expanding from one side of the cell to the other. So let's say that we have glucose, for example. Let's say it goes from one side of the cell, the apical side, and then it's going to come out, here, let me erase this. It's going to come out through the basolateral side. Transcytosis is where materials go from one side of the cell to the other. An example of this is digestion. During digestion, the nutrients that you eat are broken down to their simplest parts. They need to go from the lining of your intestines into your blood. So what they must do is, through carrier-mediated transport, they must go from one side of the cell to the other. We call this transcytosis. Trans means across. Now, we know that the epithelial cells are connected through something called a tight junction. What tight junctions do is that they're kind of like staples that keep cells together to form a tissue. Sometimes, though, these tight junctions aren't completely tight. Sometimes they leave a little bit of space between them. And there's some things, like, for example, sodium, on occasion, that can actually sneak between the two cells here. They can actually sneak through the tight junction and travel through the cell, through the cells, through the tissue. We call this paracellular transport. Para means next to. All right, let me make sure I got everything covered here. And just to clarify, when I refer to epithelial transport, that is movement either through through the epithelial cells, transcytosis, or between epithelial cells, pericellular transport. All right, and lastly, we have secretion and absorption. We'll be using these terms quite a bit. Secretion is movement toward the surface of a cell. An example of this is going to be endocrine hormones. What these do is that they go from the cells into the blood. These cells here are endocrine cells. They're going to secrete through the apical membrane, which I should add that it is from the apical side of the cell. Going to secrete hormones through the apical side into the blood. So secretion is through the apical aspect. Another example is sweat. When you sweat, you're taking water going from the basolateral side to the apical side of the cells that line your integument. Absorption is a bit different. Absorption is going toward usually the basolateral side. An example of this is going to be nutrients. What's going to happen is that in your blood, following, well, actually not your blood, following digestion, what you want to do is you want to get nutrients from the stomach, well, in this case, the small intestines. You want to get them from the small intestines into the blood. So it's going to go from the apical side to the basolateral side. So secretion is when something goes from the basolateral side to the apical side. Absorption is when something goes from the, wait, let me fix that. Secretion is when something goes from the basolateral side to the apical side. So from here to here. Absorption is when something goes from the apical side to the basolateral side. In fact, let me go ahead and clarify that. So it goes from basolateral to apical, and with this one here, absorption is going to go from apical to basolateral. Now there's something else called excretion, which we'll talk about later on. Excretion is when something is eliminated from the body. We'll talk about that later on. All right, everyone, we have finished chapter 3. It's been a journey. And what you want to do is make sure that you do the cells lab. And after chapter 4, I suggest you do the tissues lab, but you can do them any order you want. Okay, everyone, it's been an honor. See you at chapter 4.